morning, guys. I'm going to show you a little lesson here on the lead up to the molecular model building lab. So I posted the notes for Monday, and if you can give it a shot working through it, I think that would be a great 3 hours for the week for you guys. Hopefully everything's good. Happy Holy Thursday. We'll start off with a sheet that looks like this. So try to make sure you have all this stuff handy. Okay. So how elements combine. We rarely find atoms alone in nature. They usually combine with other types of atoms to form our compounds and our molecules. Each element can make a specific number of connections with other elements. This is called its combining capacity. So I want to go over that with you guys and remind you that that's simply the ability to make a bond. So it's what it does with those electrons that it has in its outer orbit. As a rule, atoms combine so that they can complete or fill their combining capacity. So the first example we can look at is the sodium bromide. So on the whiteboard, I'm going to be going through this part here with you guys. Okay. So again, super important you have your periodic table handy for all of this. It's kind of our basic tool. And I will look up sodium, and I'll notice it's atomic number 11. So I'm going to have two electrons in the first orbit, 8 in the second. I'm going to have that one valence electron kicking around in the third orbit. And for bromine, don't think we've worked with that one yet. We've got 35 for the atomic number. That's a biggie. So I believe we're looking at 2, 8, 8, and then 17 electrons in the in its fourth orbit. 1, 2, 3, 4, 5, 6, 7. So there's the 17th electron. What would happen in this sort of arrangement? Again, classic metal, non-metal situation. So we're looking at an ionic bond where this electron would join the bromine atom to complete the molecule of sodium bromine. Okay, so that's all you'd want to sketch there. I'm also going to do aluminum oxide because it's probably the toughest sort of example we do in the course. And if and when we get back to doing a final exam, you're going to see something like this on it. Okay? The logic is the same. It's just a little trickier because you're dealing with more atoms. Okay? So, our combining capacity still goes back to how many electrons something has in its valence orbit. Okay? So for aluminum, if we can quickly find that, atomic number 13, 2A3. Aluminum has 3 electrons in its outer orbit. Oxygen, as you know, has 6. We've done that a million times. This aluminum would like to get rid of those electrons. Oxygen would like to gain 2 more. Nothing looks really obvious here, okay? But if you think 3 and you think 2, those numbers basically relate to the number of atoms of the other thing that's going to help it out. Okay, so I'm going to sketch it out nice and neat with a little more room for you. Okay, it's kind of cool right now because you guys don't have to say wait. You can always just pause it and go back, right? So check this out. Let's set this up nice and symmetrically. So I've just drawn all the atoms that are going to play into this, okay? And I'm going to set up the valence electrons everywhere, okay? and I think I mentioned this back in school, the more symmetric you guys can make things, the better to help you understand and to actually draw the diagrams. Okay? At the end of the reaction here, it's not really a reaction, at the end of the event, if each atom has the right number of electrons in its valence orbit, it's happy, it's complete, it's kind of full. And the easiest way to get to that with this example is to send that electron there, that electron there, hang on, what am I missing here? Oh, I'm missing a third electron on each of these aluminums, sorry about that. This electron here, this electron here, happy, happy, and this last electron here, here, and this last electron here to here. Okay? So now, at this point, these electrons are gone for this aluminum. It's got its proper amount in the previous orbit now of 8. Gone, gone, gone. And if you look at each oxygen, you see 8 electrons in each valence orbit there. So that is what aluminum oxide would look like. Okay? So just keep that in your back pocket. It's one of our trickier examples. I wanted to go over that with you guys. And now you have it. Okay, so moving along. Towards the bottom of this now, when 2 or more atoms of the same element join, we call this a diatomic molecule. So something like oxygen and oxygen. Oxygen has the 6 electrons that we already talked about. Both atoms want 8, so if they share these electrons, both atoms are happy. And then this is what we call oxygen, O2, that's what the 2 means. Hydrogen's an even easier example. We know hydrogen has its 1 electron. It wants to have 2. If one hydrogen can find another hydrogen, they share. And then we have our hydrogen gas. Okay? So diatomic molecules look like that. Okay. So here we go. We're going to get right into our lab, our molecular model lab now. Okay? Well, actually, we'll do one last thing first here. I want to show you guys a couple structural diagrams, and that's what you're going to be doing on the worksheets through the molecular model lab. Okay? So right at the bottom here, we have H2O and O2. A couple nice, easy examples in which to show you guys structural diagrams. Think symmetry, count your atoms, plot them out, and then see how they connect. Okay, H2O, O, H, H, nice and symmetrical. We know that hydrogen has the 1 electron, and we know that oxygen has the 6. And what you're going to always be doing in this lab, we'll keep this up here, is you're always looking for 2 electrons that can be shared back and forth between the atoms. And that's going to be a bond. Okay, we call that a covalent or molecular bond. And when we set it up here, yes, it may look like some sort of Star Wars battleship from kind of a plan view, or it can look like a molecular bond. And when you do this, especially as you advance through high school chemistry and beyond, you can then get rid of those electrons that aren't part of the bond, okay, and just put them in like that. And there's your molecule, H2O, okay? Oxygen, even easier. Oxygen, oxygen. You've got your 6 electrons. they need 8. So we're looking at 2 bonds, a double bond. If you want to be nice and fancy, you don't even need those other electrons, right? You know what's happening? Ta-da! You're done. Okay? So that should help you finish up that sheet. Now I'd like you to have a look at your molecular model lab. I'm going to set you up with it, do a couple of examples, and hopefully you're good to go. As always, I'm only an email away, and we can make sure you guys don't miss out on any very important chemistry. Okay? So, if we were in school, we'd actually be having some fun putting these things together 3D. You'd have a bunch of spheres with little holes in them that you'd be connecting. Those are basically just the bonds. Okay? So whenever you see number of holes up here, we're not going to actually worry about that right now. Okay? As a fun bonus, if any of you want to find small sticks and spheres that you could connect things to and you wanted to create some and share them with the group, that'd be cool, but totally not necessary, just a bonus. Okay? So even through here, the color and the number of holes kind of represents that combining capacity we just talked about before. Okay? So something like hydrogen, I'll do this part with you here, okay? And we're gonna basically show you how many other atoms they could connect with, okay? Hydrogen has the 1 electron. It can only make 1 bond, okay, with something else. Oxygen has that combining capacity of 2. It's got the 6 electrons, but it wants to make 2 connections, okay? Chlorine, I'll have to review my periodic table for that one. 17, so it's got that need or combining capacity to want to get 1 more. So it kind of appears like a hydrogen, but it wants to get 1 more. And then for carbon, sorry, I just did chlorine. Carbon is a really cool atom, okay? And that's why you hear the word hydrocarbons so much, because it combines all the time with other nonmetals, okay? Carbon has 4 electrons in its valence orbit. It wants to connect with 4 other things, okay, to create its molecules. So it has a combining capacity of 4, okay? So now you guys are going to work through drawing the structural formulas for all these different compounds, okay? Hydrogen, carbon tetrachloride, chlorine, acetylene, water, methanol, okay? Da-da-da-da-da-da-da. I will do a couple with you. Hydrogen. I think I've already done hydrogen, right? You should be able to do this one by now. You're looking at 1 hydrogen atom, another hydrogen atom, and a double bond between them. Fix that, a single bond between them. They only have the 1 electron to be bonded with. Done. Carbon tetrachloride, CCl4. Set it up symmetrically. We know that our carbons have to have a connector all around, and our chlorines only have the 1, so this is a perfect sort of setup like that. That's what you're looking for, okay? Chlorine again, Cl2 is a diatomic molecule. Chlorine, why do I keep drawing 2 bonds? Chlorine and chlorine with 1 bond, okay? Maybe we'll pick one trickier one from further on, and I'll let you guys try to do the rest, okay? See if you can challenge yourself to do the rest. And there's an abundance of help online, and if you review the notes that I posted, that should help you as well. Okay, how about we do something like butane down here, C4H10. C4H10, a true hydrocarbon. Step 1, set it up symmetrically. Let's put our 2 C's in the middle. Now we have to put 10 H's here somewhere, right? Another way to do it is, why don't you go ahead and put your bonds from your carbons, okay? So there's our 4 C's, right? C4, 1, 2, 3, 4. And each carbon has to have a bond coming off it, okay? Spoiler alert, there's probably going to be 10 bonds, right? Because it's got to connect to 10 different hydrogens, okay? Imagine if there wasn't. I'd be deleting this whole video and going back over everything in my mind to see what the heck's going on. Okay? Ta-da! 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's your 10 H's. There's your molecule of butane. Okay? So you guys would be sketching that in there and having fun with the rest. Okay? That's it for now. You guys won't see this till Monday. Monday is a holiday, so technically I'm still going to post it, but you guys aren't really expected to get back to school until Tuesday, so hopefully you've had a great long weekend by the time you see this, and we'll go from there. Don't be shy to email me your questions and comments. Have a good one, guys.